All right, hello grade 10s. I have posted this lesson on Wednesday morning at 8 a.m. This will be the last lesson posted for this week, and because of the 4-day weekend coming up, there won't be anything else posted till next Tuesday. So before I get started, I'm also going to be posting a Google form today. And I would just like you to fill that in and just do your best with the questions. I'm not going to count it for marks. It's just so I have an idea of where people are at. So what I would have done in class is I would have asked you to give me some examples of parabolas you have come across in everyday life. So remember, parabolas look like this. And we put little arrows there to say that they keep going. Or they can look like this, upside down. Or sometimes they just start and then they go like this. Okay? There's lots of different ways these things can look. This would just be the case where we had a starting point and it didn't go on forever in the opposite direction. So let me just get into some examples. So the first example, if you've ever golfed or you know what golf is, you'll know that a golf ball travels kind of like this. That bump shouldn't be there. That's just my screen. And if you're using a driver, you're going to hit it a lot further. If you're using like a sand wedge, it's going to go way up high and then come down very fast. And all these curves are examples of parabolas. So if we were in class and someone's like, oh, when would we ever see a parabola in real life or whatever, I would just pick up a piece of chalk and just toss it across the room. And if you watch the path it follows, it is in a perfect parabola every time. And gravity's bringing it back down to Earth, and that is very much involved. If you've ever played Angry Birds, you've seen parabolas. I know this game's pretty old now, but I feel like it's still out there. And you have to adjust your parabola to hit the monkey or the stuff up here, whatever you're trying to do. So if you played Angry Birds, you've dealt with parabolas a lot. And we can put a grid over top, and then we can talk about the vertex. So about here. So the vertex of this Angry Bird shot would be 20, comma, about 20, maybe 21. We could talk about the zeros being down here, and then again it would have a zero when it hit the ground, somewhere over here. The axis of symmetry would come right down the middle, etc. And so you would use that knowledge in Angry Birds to aim your parabola to get it to hit something. Red Bull does a lot of interesting stuff, and it all ends up being parabolas. They have dirt bikes jump over stuff, and we've got a clear parabola here. You can see the vertex is right here at 6, 5. So that would be like 6 feet or 6 meters that it's moved forward, and it's gone 5 meters in the air from when it started. We've got this dirt bike jumping over this canal here. Again, there's a parabola there. The vertex is around here. And equations define these things. We're not at the equation part yet. We're just sort of getting started. Next one, another Red Bull thing. This is a huge dirt bike jump. Again, you can see the parabola here. You can imagine the vertex as the highest point. And that's a lot of what today is going to be. Here's a snowboarder following a parabola, of course, and its vertex is about here. We could say its zero is over here where it hits the ground. You don't need to be taking notes. Just watch. Here's a car jumping over a marina, and then we've got its vertex about there, its max height. And here we go. We are now into the handout. What I did today, there's a lot of handouts today. You've had 2 pretty short lessons. This will be a longer one and the last one for the week. I spelled balloon wrong here, it looks like. There we go. Okay, so this is your handout. I'm going to work through this. We'll do this together and this together. I'm going to have you do this as part of your homework practice, and then I'll do this, and you'll do that. So hopefully we won't be too long here, and you can enjoy the rest of your week once everything is all done. Okay, so we got a little football guy here, and we're going to say that he's punting the ball, an onside punt or something, I don't know. But typically punts go not as far if they're an onside punt, and they could go really high. None of this really matters, of course. Let's see if I can recognize it as a shape. I cannot. All right, so we are going to talk about what all the different parts of a parabola mean in real life. So first of all, the vertex of this parabola, and I'll color code, is going to be right here in green. And the vertex tells us the max, height and when the max height occurs. The minimum maximum value, that is just the max height. Okay, I'm just going to copy and paste the font here. The axis of symmetry is going to tell us when the max height occurred. And this could be minimum height as well, depending on the situation. So let me label these things. So the maximum or minimum, computer's getting a little glitchy here. So that's going to be the max. And then this here is going to be the axis of symmetry, or I'm going to abbreviate that, AOS. I know a lot of you don't like to write a lot, so that's what we will do. The y-intercept, so if we drew in a grid here, and let's say the ground is here, the y-intercept, I'll do in purple. No, I already used purple. I will use, tell you what I'll do. I'll make the curve black, and I'll use red for the y-intercept. There we go. I'll use red for the y-intercept. So the y-intercept is going to be right here. And what the y-intercept is going to tell us, I'm going to steal this, is it's going to tell us the starting height of the object. Okay? So here it starts a little bit off the ground. And the x-intercepts, or the zeros, one of the most important parts of all this. Let me steal some pink here. That's going to be, that's not pink. That right there is going to be one of the zeros. You might remember from yesterday that we often have two zeros. Sometimes we have none. In this case, we only have the one. And this zero here is going to tell us, you can imagine it landing there, so this x-intercept or zero is going to tell us when the ball or object hits the ground. And remember, x-intercepts are zero and zeros are the same thing. So the x-intercepts and zeros tell us when the object or the ball or whatever hits the ground. And this point here was nothing. That was just me testing my pen. Okay, so let's move on. We will do one example, and then you will do one, and then same thing. So Michaela is shooting her new bow and arrow into the air to try to hit a helium balloon. The graph represents the path of the arrow. The x-axis shows the distance. So you know what? I'm going to write down here distance, because this is the x-axis in meters. And the y-axis shows the height in meters. Okay, let's answer a few questions here. I'm going to have to go 2 pages up at once. The vertex. The vertex is right there. X value looks like it's 30. And the y value looks like it's 110. The zeros, we've got one back here at -15. And we've got another one, remember the zeros are where it hits the ground, or when y is 0. And the y-intercept is there, and it's 60. Okay, now I would love for you to try to answer these 4 little sentence questions here. I'd encourage you to pause it right now, try to answer those, and then come back and see. Okay, so hopefully you tried it. Now let's answer it. What's the highest point that the arrow reaches? Well, that's the vertex. And in this case, it looks like it's 110 meters, which of course we could have got from the vertex. How far away is the arrow when it reaches its max height? So here's its max height. For its distance, we come down here, and it's 30. And again, we could have got that from here. This is the max. When it reaches its maximum, that's the axis of symmetry, of course. You could draw that in there if you wanted. Where was Michaela standing when she fired the bow? This is the hardest question. So when she fired the bow, that's going to be at distance 0. So this is when it starts, right? So right here, this is where she was standing. So she was at 60 meters above the ground. So maybe she's on top of a building or something above the ground. Maybe she's on a cliff. Who knows? How many meters did the arrow travel horizontally? So we want to know when it hits the ground. So when it hits the ground, we start here, the arrow goes up, and then it starts coming down, it hits the ground here. So 75 meters. Ooh. Okay, so 75 meters is how far it traveled. And then if we look, we never talked about this point here, this minus 15. And that's because that point, it doesn't really exist. She shot the arrow from here and it went up and came back down. But we can imagine, because these parabolas are symmetrical, we can imagine it going back from here. So if she shot it from the ground, it would look like this whole thing. But because she didn't, the yellow part here is the path of the arrow. Okay, so there is a second question that's very much the same. Same table, same sort of questions. I'm going to leave that for you for your homework. And at 3 o'clock today, I'll post a file that has the solutions in it. Okay, so please go ahead, try this one, and then the answers will be posted later on today. Okay, so this is the last thing I'm going to do, and then I'm going to get you to do the last question on the page. All right, so this is called curve fitting. The idea here is that we're given a bunch of data. We're going to plot all the points in here, and then we're going to draw a curve, a parabola, that fits the best. So I'm going to do the first 2 points, and then I'm going to pause. Well, I'm hoping you'll pause, and you'll do the rest. So the first one is 1950, 372, so there's 370, there's 390, so I don't know, about there. Again, it's not important that they're crazy accurate. 1951, 300, and let's say about there. Okay, so I encourage you to pause, do all the rest of the points, and then unpause and see how you did. If you're going to pause, please pause now. All right, so I did my best to plot the points. Hopefully yours looks something like this. Now we've been asked to do a parabola of best fit. Now, I haven't actually told you what that is, but you can probably guess. It's just a curve that does its best job to look like a parabola and go close to the points. So if I'm going to do that, I'll try it like this. That's not great. It looks like it's a little too high, so I try it again. Nah. Ugh, this is a lot easier to do on my board in the classroom. I just keep overshooting that second part. There. That's as good as I can do. This isn't perfect, obviously, but that's how I'm going to do. Now, the important part, the most important part of this, is that from this point forward, we don't care about any of the points. So you can imagine all those points are gone, and we're only looking at the black line. Okay, so to answer these questions, we use the black line. So first of all, it says, what's the vertex? So that looks like it's here. So that looks like, let me use a different color here so you can see it. It looks like it's 1960, comma, and then we go over here. Well, what's that? 480, let's say 475,000. What does the vertex represent? Well, in this case, it represents the maximum number of births and the year that it happened. Okay. In what year did the births reach a maximum? Again, we're not using the data points. If we use the data points, our answer is 1959. Okay, but we're using the curve just to do a general idea of what's going on. And according to our curve, which isn't perfect, the answer is 1960. What was the maximum number of births? Again, we go back to our vertex, and it looks like, according to our vertex, it was 475,000 births. And is this parabola useful for predicting births into the future? So this is a question for you. Do you think Because remember, these parabolas speed up. Do you think that the number of births continue to go down at this alarming rate? What do you think? So this is the baby boom. This is essentially what you're looking at. My parents were born in 53, so around here. And the number of births just kept skyrocketing. It was after the war. You've probably heard about it in geography, maybe history. And then the number of births started to come down. So is it accurate for predicting the future? Probably not. Birth rate does not decline forever. So for example, those baby boomers children like myself, there's a lot of us because there were a lot of baby boomers. So when the baby boomers started having kids, there would have been a spike as well. And you can look up Canadian birth rate over time if you want. Okay, so I did it, and we looked at the years between 1950 and 1967. So that's about here to here. So we only looked at this section, and it looks really much a lot like a parabola, but then if you follow it, it does weird things after that, right? It bumps and it's falling fast and then it slows down. So to answer the question, probably not. Birth rate does not decline forever. But it did a good job over these 17 years. Okay, so the last thing I want you to do is do the same thing here. This is with cases of HIV infection. The numbers are easier. They're easier on this one than the one we just did together. So give that a shot, and again, the answers will be posted at 3 o'clock. Okay, good luck, folks.